Okay, so hi everyone and welcome to Honors Chemistry. I hope you guys are having a lot of fun in this class, whether you're preparing in the summer or you are trying to cram last minute before a test. It's all fun. So this is just the first video in a series that's going to be examining the Honors Chem curriculum from Chapter 1 to Chapter 18 and Organic Chem and everything else in the textbook. So just stick along and you will have a lot of fun with chemistry. Chapter 1, let's go. Okay. So, Section 1 of Chapter 1, Chemistry is a Physical Science. So first we have to discuss what is chemistry. Before we get any further in actual honors chemistry, we have to know what chemistry is, right? So chemistry is the study of composition, structure, and properties of matter, the processes that matter undergoes, and the energy changes that accompany these processes. And there are 6 main branches of chemistry. So the 6 branches are as follows: organic chemistry, which is the study of most carbon-containing compounds. Then next we have inorganic chemistry, which is the study of non-organic substances. And inorganic chemistry is mainly what you're going to be dealing with for the first semester of honors chem, whereas the second semester is more focused on physical chemistry. And physical chemistry, that is to say the study of properties and changes of matter and their relation to energy. Next, our 4th type of chemistry is analytical chemistry, which is the identification of the components and composition of materials. Next, biochemistry, the study of substances and processes in living things. How does chemistry incorporate itself into every aspect of our living life on Earth, inside human beings, inside animals, inside plants? That's all biochemistry. And lastly, we have theoretical chemistry, which is using math and computers to understand principles and design and predict the properties of new compounds. So theoretical chemistry is often connected very deeply to researching things using these technologies to find out how we can improve chemistry on our understanding of how chemistry works. And in order to do that, we have to do research. And there are 3 main types of research that we go through as chemists and as scientists. So first we have basic research, which is carried out for the sake of increasing knowledge. For example, if you were to by chance discover a new compound, that would be basic research. Maybe another example of basic research would be if I were to wonder what's going to happen if I cut off my pinky finger. And this is basic research because this really isn't going to give you any physical benefit. By cutting off your finger, you're essentially just signing yourself up for a life with 9 fingers and a lot of pain, but you're going to increase the knowledge that you have of how it is to function in life with 9 fingers, what it feels like, what's the pain like, how does it, like, what's the mind experience or whatever of cutting off your finger. So that would be basic research, something that you just do to learn something, which is, I guess, like the point of a lot of your labs in honors chemistry. You don't really gain anything out of it except knowledge. You're seeing how these concepts that you learn in your textbook apply themselves into the real world. That's going to be basic research. Next, we have applied research, which is carried out to solve a problem. For example, all the researchers across the world right now that are researching cures for the coronavirus are doing applied research. There's a problem that already exists in the world that they have to solve. So they're applying fundamentals of chemistry to this real-life problem and trying to solve it in a real-life time frame. Lastly, we have technological development, which is, I guess, like the most fun type of research because you're trying to produce things and use products that are meant to improve your quality of life. For example, the development of the iPhone is an example of technological development. We already had telephones before the iPhone. We didn't really need the iPhone in our lives, but once it arrived in our lives, we all benefited from it. For example, every time you play a video game on your phone, you're enjoying an improved quality of life than you would have had if you were just using a flip phone. So although you didn't gain knowledge from using an iPhone versus a cell phone, you're gaining an improved quality of life, which is the point of many technological development and technological discoveries and research, because you're just trying to improve the human life experience for other people, which is kind of cool. Section 2 of Chapter 1 is going to be matter and its properties. So it's important, as soon as you enter basic honors chemistry year 1, you should know what matter is. So there are kind of like some basic units of matter that you have to know before we start to discuss other things. So first, let's discuss the atom, which is the smallest unit of an element that still maintains its chemical identity. If you were to break up an atom, you get subatomic particles, electrons, neutrons, protons. And those are no longer an atom, those are particles within the atom. So you can't really say that it maintains the integrity of the element that it came from. So the atom is essentially the smallest unit you can have that's still an element, that's still its own thing, its own substance. Next, there's an element, which is a pure substance that cannot be further broken down. Take the example, if I had a block of, like a solid gold bar, if I were to cut that in half, it's still a gold bar, it's still gold. If I cut that in half, it's still gold. Even if I keep breaking it down, it's still going to be that same pure substance. So that's exactly what an element is. It's a pure substance that cannot be further broken down. And lastly, we have a compound, which is a substance that can be broken down into simpler substances. And that's going to be made up of the atoms that are of two or more elements that are chemically bonded. So for example, H2O, water, is made up of hydrogen and oxygen. If I were to break up the compound of water, I would get these two elements, hydrogen and oxygen. So I can break down this compound into two in this case, two different elements that are bonded together in a polar covalent bond to form water. Now we can discuss properties and changes of matter. So there are two types of properties of matter, which is extensive and intensive. An extensive property depends on the amount of matter that is present at the time. For example, volume and mass, they depend on the amount of matter. If you have more matter, you're going to have a higher volume and higher mass. If you have less matter, you'll have a lower volume, lower mass. And then there are intensive properties, which actually do not depend on the amount of matter that is present in whatever thing that you're looking at. For example, physical characteristics like color or smell or texture, melting point and boiling point, density do not change depending on the amount of the thing that's there. For example, if I have a cup of water, the density of that cup of water is going to be 1 gram per milliliter. If I pour half of the cup out, it's still going to be 1 gram per milliliter because it did not change based on the amount of water present. It just depended on the actual composition of the water and what it was. Next, we know that physical properties can be observed without changing the identity of the substance. Whatever you do to a physical change does not actually change its identity. For example, cutting something or bending something doesn't actually change fundamentally what something is. So now when we're discussing these changes, we have to do it in the context of states of matter. States of matter, you know the three main ones, which are solids, liquid, and gases. So solids, they have a definite volume and a definite shape. For example, if I have a table that has a definite volume and a definite shape, whatever I do to that table, it's still going to stay the same shape, it's still going to stay the same volume. I can't really change that depending on like what container it is or anything. Next, we have liquids, which have a definite volume but not a definite shape. If I pour 1 liter of water inside a bowl, it's going to fill its shape to that bowl. If I pour that same 1 liter of liquid into a glass, it's going to fill the shape of that glass. So its volume is definite, but its shape is not. Its shape changes based on the size and shape of its container. Lastly, we have gases, which have a neither definite volume nor definite shape. If you think about the air all around us, that's an example of a gas. If I have a closed box with some air inside it, the air is going to expand to fill the volume of that box. But the moment that I open that box, the air is going to escape and it's going to fill the entire volume of the room that that box was previously in. So it doesn't really matter what volume of gas you have, it's still going to take up the entire volume of or shape that it is in. And the reason why that occurs is because as you progress from solid to liquid to gas, your intermolecular forces decrease and your degree of randomness will increase. So if you think of the particles inside a solid, they're going to be very closely together and very orderly and organized in their structure. And that means that it's going to stay in a solid shape and you can't really change the shape or volume of a solid because all of its particles are clumped together and held together by their stronger intermolecular forces. But as you progress to a liquid and gas, the particles inside are going to be able to move against each other and move around and expand. The intermolecular forces are decreasing so that you have these indefinite shapes and indefinite volume when it comes to gases. And so the degree of randomness of these particles increases as the volume increases and as the intermolecular forces decrease. And that's how you have all this range of solid to liquid to gas in all of its particles that are inside. The fourth state of matter is not as commonly discussed in introductory honors level chemistry, but it's important to know. So it's plasma, which is a high temperature state of matter in which atoms lose most of their electrons. Now let's discuss chemical properties and chemical changes. We already discussed physical changes, so now let's discuss chemical properties and changes. So chemical properties relate to a substance's ability to undergo changes that transform it into a different substance. And here are 5 conditions of a chemical change. So a color change, a formation of a precipitate, formation of a gas, a color change, or a temperature change. And if you're just wondering what a precipitate is, it's when you mix two aqueous solutions and form a solid. Obviously, that's not going to happen naturally. It's going to happen in a chemical reaction, which is how we know it's an indication of a chemical change. So now let's discuss the elements, which is section 3 of chapter 1. So a type of element would be a metal. A metal is an element with a high conductivity of electricity and heat. They are malleable, which means that they can be rolled into thin sheets. They are ductile, which means that they can be drawn into a fine wire and manipulated. And they have a metallic luster, which is usually silvery gray or white. Like in the example of this picture right here on the right, it has a silvery gray luster. Metals also have strong tensile strengths, which means that they resist breaking when they're pulled. If you pull a metal, it's not going to break. And lastly, remember that metals are solids at room temperature. Next, we have on the periodic table nonmetals. So nonmetals are various states of matter at room temperature. There can be gases, liquids, or solids. For example, iodine is a solid, it's a nonmetal. There can be liquids on the periodic table, like bromine is the only liquid in a certain region of the periodic table, and there can be gases like helium or hydrogen, which are all nonmetals. The main characteristic of a nonmetal is that, unlike a metal, it is a poor conductor of heat and electricity. Its characteristics depend on its location in the periodic table, which determines other things about the nonmetal. Lastly, next we have metalloids, which are elements with some characteristics of metals and some characteristics of nonmetals. They are solids at room temperature. They are less malleable than metals, but not as brittle as nonmetals, and they are semiconductors of electricity, which means that their ability to conduct is between that of metals and nonmetals, in between both types. And lastly, we have noble gases, which are the elements in group 18. Noble gases are very low in reactivity, and they're gases at room temperature. The reason why they have a low reactivity is because they're very stable elements. You'll learn this later on, but they are really stable in their octet configuration, so they're less likely to give up electrons or gain electrons to form new compounds. So they're really content in their location, which means that they don't really react with things, and they're inert, which means that they're chemically inactive. And lastly, they are conductors of electricity. So thank you for watching this video on chapter 1 of Honors Chem. This is a pretty short one because chapter 1 is pretty straightforward. So I hope you guys enjoyed it, and if you liked the video, make sure to keep watching, like, comment, and subscribe for more fun chemistry content. So yeah, thank you guys.